Good morning, students. Our today's topic is monotonic sequences. So first definition, what is monotonic sequence of self-adjoint linear operators on a Hilbert space? So let us take a Hilbert space H and a sequence of self-adjoint linear operators Tn. Then we say that the sequence Tn of the self-adjoint linear operators on the Hilbert space H is monotonic sequence if it is either increasing or decreasing. If it is increasing, it means T1 is less than or equal to T2, less than or equal to T3 and so on. And monotonically decreasing means T1 is greater than equal to T2, greater than equal to T3 and so on. So any sequence which is either monotonically increasing or monotonically decreasing, that is called monotone sequence. Now there is a remarkable property of the monotonic sequences which is given by the following theorem. So the theorem is, let Tn be a sequence of bounded self-adjoint linear operators on a complex Hilbert space H such that T1 is less than or equal to T2, less than or equal to T3 and so on, less than or equal to Tn and so on, less than or equal to K. Here this K is bounded self-adjoint linear operator on H. Now suppose that any Tj commutes with K and with every Tm, then we are to prove that the sequence Tn is strongly operator convergent. Strongly operator convergent means Tnx converges to Tx for all x belonging to H, and then we are to prove that the limit operator T, that is a linear bounded self-adjoint operator and satisfies the partial ordering relation T less than or equal to K. So first of all, let us define Sn by the difference of K with Tn. Now we prove the theorem in two parts. In the first part, we prove that the sequence formed by the inner product of Sn square x with x that converges for every x belonging to the Hilbert space H. In the second part, we prove that the sequence Tn is strongly operator convergent where T is linear, bounded and self-adjoint. So first of all, let us prove the first part. To prove the first part, now because Sn is K minus Tn, K and Tn both are self-adjoint operators and therefore Sn is also self-adjoint. Now let us consider the operator Sm square minus Sn into Sm. Now taking Sm common, this can be written as Sm minus Sn into Sm. Substituting the value of Sn and Sm which we defined in the first step of the theorem, Sm is defined by K minus Tm. So putting the value here, this will become Tn minus Tm into K minus Tm. Now we are to show that this operator, that is a positive operator. So in order to show that this is positive, we will have to show that these two operators, they commutes. Now first of all, we show that these are positive operators. Now because for m less than n, Tm is less than Tn, because we are given in the statement that T1 is less than or equal to T2, less than or equal to T3 and so on, less than or equal to K. So from this equation, we can say that for m less than n, Tm is less than Tn, and so Tn minus Tm, that is positive, and also from here we can say that k minus tm, that is also positive. Now we show that these two operators commutes. So let us consider the product of tn minus tm with k minus tm. Now simplifying this product can be written as tn into k minus tn into tm minus tm into k plus tm square. Now because k commutes with tn, so this can be written as k into tn. These two also commutes with each other, so this product can be written as tm into tn. This can be written as k into tm, and this term is as it is tm square. Now we can combine these two terms and taking k common from there, and from these two terms taking tm common. So we are left with k minus tm into tn minus tm. So we can say that the two operators tn minus tm and k minus tm, they commutes. So by the last theorem, which was product of positive operators, so by that theorem their product is positive. So from this equation 1, because these two operators commutes and therefore this product is positive, and therefore we can say that this operator is positive operator. So we can say Sm square minus Sn into Sm is positive operator. It means Sm square is greater than or equal to Sn into Sm for m less than n. In the same way, if we consider Sn into Sm minus Sn square and repeating the same steps, we can show that this operator is also positive operator. So from here we get Sn into Sm is greater than or equal to Sn square. Now we can combine the equation 2 and equation 3. So combining the two equations, we get for m less than n, Sn square is less than or equal to Sn into Sm, and that is further less than or equal to Sm square. Now by using this result, we will prove that the sequence formed by the inner products of Sn square with x, that is a monotonically decreasing sequence of non-negative numbers. So let us consider the inner product of Sm square x with x. Now by using the last equation which we proved, Sm square is greater than or equal to Sn into Sm for m less than n. So using here, this product will be greater than or equal to inner product of Sn into Smx with x. Now again further, Sn into Sm is greater than or equal to Sn square. So this product will be further greater than or equal to inner product of Sn square x with x. Now this can further be written as inner product of Snx with itself, and by definition inner product of Snx with itself, that will become the square of norm of Snx, and this is non-negative quantity. So we have proved that this sequence with fixed x is a monotonically decreasing sequence of non-negative numbers, and so this sequence converges. Now this completes the first part of the theorem. In the second part, we proved that the sequence Tn is strongly operator convergent. Now because we are given in the statement that every Tn commutes with every Tm and also with k, and therefore we can say that all the Sj's, they commute, and also these operators are self-adjoint operators. Now minus 2 into inner product of Sm Snx with x, that is less than or equal to minus 2 into inner product of Sn square with x, and this is obtained from this equation number 4 from here. So we will use this to prove that the sequence Snx is Cauchy. So let us consider the square of norm of Smx minus Snx. By definition, norm square means inner product of this element with itself. So this can be written as inner product of Sm minus Snx with itself. And this can further be written as inner product of Sm minus Sn whole square x with x. Now expanding this whole square, we get inner product of Sm square x with x plus inner product of Sn square x with x minus 2 times inner product of Sm Sn x with x. Now by using this equation 5 here, so we get Smx minus Snx norm square approaches to 0 as n and m approaches to infinity, and this proves that the sequence Snx, that is a Cauchy sequence in H. Now H is Hilbert space, so that is complete norm space, and therefore every Cauchy sequence in H is convergent. So we can say that the sequence Snx, that is convergent sequence. So by the convergence of this sequence, we can say that the sequence Tnx is also convergent, because Tn is given by k minus Sn. So let us take this sequence converges to Tx for every x belonging to the Hilbert space H. So from here we can define an operator T from the Hilbert space H into itself, and this operator is a linear operator. Now we will prove that this operator is self-adjoint, bounded and less than or equal to k. So first of all, we prove that T is self-adjoint operator. To prove T is self-adjoint, we prove that T is same as its adjoint. So for this, let us consider the inner product of Tx with y. Now by definition, Tx is the limit of the sequence Tnx. Now this limit can be taken outside of inner product, so this will become limit inner product of Tnx with y. Now if we take this in the second argument, this will become Tn star, but because Tn is self-adjoint, so its adjoint will be identical with itself. So Tn star is same as Tn. So inner product of Tx with y becomes limit n approaches to infinity inner product of x with t and y. Now this limit can be taken here in the second argument, limit of t and y. So that is ty, and again taking t in the first argument, this will become inner product of t star x with y. So this proves that t is same as t star, and this proves the self-adjointness of the operator t. Now in the next step, we prove that t is bounded. To prove t is bounded, we will use uniformly boundedness theorem. According to uniform boundedness theorem, if we have a sequence Tn of bounded linear operators from a Banach space X into a norm space Y, such that the sequence of norms of Tnx is bounded for every x belonging to X, then the sequence formed by the norms of Tn that is also bounded. So by using this theorem here, because here our sequence Tnx that is convergent and also bounded for every x belonging to H. So by this theorem we can say that the operator T is bounded. Now in the last step we are to prove that T is less than or equal to K, and this is the partial ordering relation which we defined yesterday. Now according to that definition of partial ordering, T less than or equal to K means inner product of Tx with X is less than or equal to inner product of Kx with X for every X belonging to H. Now because Tn is less than or equal to K, so by definition of partial ordering we can say that inner product of Tnx with X is less than or equal to inner product of Kx with X. Now because this is true for every n, so we can say that its limit is also less than or equal to inner product of kx with x. Now this limit can be taken inside in the first argument, limit of t and x, and the limit of t and x, that is tx. So this proves that inner product of tx with x is less than or equal to inner product of kx with x. And by definition of partial ordering, this proves that t is less than or equal to k. So we have proved all the steps. T is linear, T is self-adjoint, T is bounded, and also T less than or equal to k. And this completes the property of monotonically increasing sequence.